Hi, my name is Harsha Patel, and today we will be discussing Lab 5, Magnetic Braking with Faraday. Some of the fundamental concepts we need to know for this experiment are the magnetic field of a bar magnet or the magnetic field of a dipole, Faraday's law, magnetic flux and EMF, and how EMF is related to magnetic flux in dI/dt form, so the derivative of flux over time. Ohm's law, magnetic force on a falling magnet due to a loop with current, Lenz's law, and the principle of momentum. Some of the measurements needed for this experiment included the length of the tube of aluminum foil, which was 0.32 meters, the width 0.005 meters, the inner radius 0.03 meters, outer radius 0.035, magnet mass 0.025 kilograms, and the magnetic dipole moment was measured to be 3.42 from Lab 3. So the average time it took for the magnet to fall through the tube during the experimental trials was 0.522 seconds, but the experimental time via the computational model was 0.321 seconds. These are some formulas that we need to know for this experiment. We won't go over them in detail right now, but we will be using them to analyze our data later. So in steps 1 and 2 of the code, we define the lengths, the width, radius of the tube, and then in step 2, you can see that we're using the formula from earlier. The magnetic field equals mu over 4 pi times 1 over r cubed times 3 times the dot product of mu and r hat, or the unit vector, times r hat minus mu. So this can be seen in the code in step 2. This slide of code in steps 3 and 4 make use of the formulas of the derivative of flux and equating the current to the derivative of flux, or EMF, over resistance. And finally, steps 5, 6, 7, and 8 make use of our formulas from before: the force on the loop, the force due to gravity, the vector position vector, and then the velocity vectors. So for our results, we have the graph of the computational model, as well as an image of what the simulation looked like. On the right, the simulation looks as though we only have the blue in it. However, there is red and blue. It's just that the simulation occurred too quickly, or in less than a second actually, so I was only able to capture the end result. But you can see that this is because it took the magnet in the computational model 0.321 seconds to fall through, which is slightly smaller than the measurement we got for our real life example, which was 0.522 seconds. Now the graph on the left depicts the velocity of the magnet falling through the tube over time, and we can discuss that going forward. So here are some questions from the interpreting the simulation portion of our lab. So how do we know whether the red or blue currents indicate clockwise or counterclockwise? We know that the red is counterclockwise and blue is clockwise due to Lenz's law, because this corresponds with what slows the magnet down. And what happens to the dynamics of the system when we flip the magnet? Well, the current would flow opposite to what we see, but the magnet would still slow down. And comparing the real world system to the computational model, our computational model was slightly off in the sense that it was more accurate. It provided a faster time for the magnet to fall through the tube. So to combat this in the real world, we would split the rod that we have into more coils so that we could be more accurate with our calculations and to account for air resistance or remove air resistance. And what does the shape of the velocity versus time graph indicate? Well, the forces are unbalanced when speed is increasing, and even more so during decrease. But since the period of time that the magnet fell in my experiment was so short, we only see this really rapidly, more steep slope, as opposed to seeing a plateau in the middle, as other examples of this lab might demonstrate a flat portion of about 1 second of balance in the middle. And now to answer some discussion questions. If the resistivity of the conductor was reduced as close as possible to zero, the dynamics of the falling magnet would change because the braking force would increase to a point where gravitational force balances out, which would prevent the magnet from falling through the tube. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? It would disrupt the normal flow of current through the rings in the current in the tube, and the braking force would likely not be as strong due to the reduced amount of current through the tube.